All right. Good morning, class. Happy Wednesday. So, I guess for today's class, I'm going to just go over, good morning. I'm going to go over content or continue from last time's material. So we'll have probably a new assignment. I'll have it posted up sometime during the weekend. It'll involve binary trees. And of course, in our Monday's class, I will spend time talking about the assignments. So that will be kind of the plan for that. Our midterm is going to be on that week 8. It's not going to be not next week, but the week after. On that Wednesday, we'll have our midterm. So for this class, obviously, it will be online. So you're going to take the sort of the exam online on web campus. Same format like in the previous semesters. So if anybody here is in the in-person class, we'll have to figure out how that's going to work out. So I have some time to sort of put that together and see how it's going to work. Anyways, that's the only announcements for right now. So let's go ahead and begin today's lesson, I guess you can call it. All right. So last time, I believe I was talking about search structures, or in this case, binary search trees, where basically every search structure always has a key value pair, but we're not going to really consider the value field for this. We focus mostly on just a key, just to see how we can maintain a binary search tree. So for binary search tree, all we have to do is maintain the following sort of property where every node, the left child has a smaller key value and the right child has a larger key value. If we can maintain that, then we can maintain a binary search tree. So because of that, the find function has an improvement over the regular binary tree version of the find function. So the idea is that we're searching for a key in our, I guess S will be our key, I suppose, in this case. So since we know that elements, the key values are arranged in a certain way, that means, for example, let's say we're trying to find, let's say I want to find 10, for example. So I start from the root and I compare this S value 10 to our key value. And since 10 is less, that means we know for sure there's no way 10 can appear on the right side. It must appear on the left side. So we can automatically jump to the left. And all the elements that are right at 15 are automatically going to be eliminated from our search. So somewhere on the left side, the left subtree of 15, so somewhere over here is where 10 has to be. So now we jump left side, look at 7, and we see that 7 is less than 10. So the elements to the left of 7 are going to be eliminated from our search. So we try only the right side. And we see that, well, we found a match, so return true up the tree. That's all we have to do. So in the regular binary tree traversal, what you would have to do actually is, well, if you look at one side, if it's not there, you try the other side. But here, we don't have to worry about that. So same idea. So in this example, we have for trying to find 16, 16 is not in our binary search tree. So we go ahead and check the root 15. 16 is bigger than 15. So if 16 does exist in our tree, it must appear on the right side. Then for 20, the right side of 15, since 20 is larger than 16, so if 16 does appear in our tree, it must be on the left side. And we see left side is null, so we can conclude that 16 cannot be in our tree. So for regular binary tree traversal, it would actually try the left and the right side. So if the left side does not find 16, it would then try the right side, and then it would OR the two results. But here there's no purpose of that, because if, let's say, 16 does not appear on 20's left side, then that's it. There's no way 16 can be in this tree. We don't have to check the right side. I mean, we could, but there's no point, because we know we can assume it's a binary search tree. 16 cannot be there. So this has a runtime of, well, regular binary tree search, which we did last week, was O of n no matter what. It was always O of n. We had to go through every single node in order to determine if the element was in our tree or not. But for binary search tree, well, it depends on the height of our tree. Now, in our binary tree sort of analysis, we know the height could be O of log n. So if a tree is nice and balanced, then this runtime will be log of n. We'll take at most the height of the tree number of comparisons or number of steps to find the element. But the height could be O of n, unfortunately. So that's the bottleneck really for binary search trees, is the height really. So in this case over here, the height is pretty nice and balanced. So we will take at most 1, 2, 3, 4 steps the most it will take to find if an element is or isn't in our tree. So that's kind of the improvement of binary search trees over just regular binary trees. So I went over insertion code last time, which this one's a little bit really strange code, but this does definitely work. Zoom out a little bit. So for insertion, we simply just have to find where in the tree is a vacant spot for element to be inserted. And once we find a vacant spot, create the node there, and that's it. So for insertion, we have to do a find operation, essentially. We're doing a find, and we find a vacant spot. So that's how this works. So let's say, for example, I want to insert the node, I want to insert the key 9 into my tree. So obviously, looking at this tree right here to the right, obviously 9 would have to go over here. So what we have to do is find, well, where does 9 have to go? Well, we see a 9 is less than 15, but it's less than 15, then 7, less than 10. And 10's outside is null, so 9 can only go in that one spot. So that's what's going to happen. But we'll go over the actual code as to see how this actually happens, but that's what we're doing. In layman's terms, that's the result of an insertion. Let's go ahead and trace out the actual code to see if we can make sense of all this. It is kind of strange code actually, so I'm going to try my best to be very slow with this trace. So let's go ahead and insert 9 into this binary search tree. So what we would do at the very top level in main, we go ahead and say root equals insert. Maybe actually I'll zoom in. Actually, no, I'll keep it like this. So root equals insert root 9. That's how this would actually be called in our program. So then R would point to that node. As always, we start from the root and we check. Is R equal to null? It's not equal to null. Then we check. So the K value, in this case 9, isn't in fact going to be less than R arrow key. So then this is going to execute. So anyway, now we have our key. So we check the key value, so it's less. So we're going to actually write here. I want to write this to the left side because it's a little bit confused. I can probably fit it here if I can. So we're going to have R arrow left equals insert R arrow left, then 9. So at this level, we're going to end up calling this function. At this level right there, we're going to end up calling this R left equals insert R left K. Okay, so this function will halt temporarily, and then we're going to now have R pointing over here. So we check. R is not equal to null, and key value actually, which is 9, is going to be larger than R arrow key. So 9 is bigger than 7, so that means 9 has to be inserted somewhere on 7's right side. Okay, so we're going to be stuck right here. So I'm going to write this to the left. It's going to be actually R arrow right equals insert R arrow right 9. So at this function instance, at this level, where R points to 7, we're going to essentially call that function. We're going to be stuck right there. We're going to be stuck right here in this function call. So we have to call insert once again. So now R is going to point to that node. Now we check. Okay, well, is R equal to null? It's not equal to null. So we check. Well, R arrow key is going to be sort of less than K. So K is going to be, no, sorry, no. k is going to be actually less than our arrow key because 9 is less than 10. So we have to insert this 9 value to the left side of r. So right here at this level, we're going to end up calling r left equals insert left 9. So at every single level, we have r pointing to a node, and we're going to either call r left equals insert r left 9, or we're going to call r right equals insert r right 9, depending on whether this 9 value is bigger or less than the element at that level, at that node. So we have to go through these paths, basically. And now, for this element to the left of 10 is going to be null. So now r equals null at this level. We had r is 15, went to the left, then 9 was larger than 7, went to the right, and then 9 was less than 10, we went to the left. So now we're at this level where r is null. So we hit this base case finally. So we found that vacant spot where 9 has to go. So what happens now is inside of this if statement, we're going to create a temporary node, temporary pointer, sorry, call this temp. And it's going to point to the left a little bit more room. Temp equals, sorry, it'll point an actual node. That's what happens. So we say temp equals new bin tree node. We assign the key to be whatever k is, and k in this case will be 9. So we assign 9 to that node. We set temps left and right to both be null because this in fact is going to be it's going to be a new leaf node, obviously. So it set the left and right to both be null. And then also we could set the value field to something, but we're not going to worry about the value field for right now. We focus only on that search key field. So after we assign 9 to the node, we return temp. Okay, so at this point, temp is now gone. Return temp. Okay, so let's go back to the previous function call at the previous level. So you go back to the previous level, we're not going to be back over here where r points to 10. So we're not stuck on this line in this function call. So we called insert r left. What did it return? Well, it returned the address of node 9 because at the very end of the function call below, we returned temp. So that address of 9 is returned up, and r left will be assigned to that. So that links the this parent to 9. So then what's going to happen is, okay, so after we do r left equals insert, we're stuck right there. Now we're going to simply return r. So returning r means we're going to return the address of that node 10 because we're at that level right there. All right, so now what happens is we go back to the previous function call. We go back over here. Go up a level, just like doing in order and pre and post order, same ID. We go back up a level. We're gonna end up continuing from this spot. Okay, so we call insert recursively. What does this insert function return? Because it returns a pointer, correct? It returns some kind of pointer. So it returned r from the previous level. So it returned that node. The address of a node 10 was returned back up to the parent. And then the parent will catch that result. So the parent will set r right to be whatever this insert function returned back to us. Well, we returned the address of 10, so we're going to reassign 7's right side to point to the same node we pointed to already. Which is fine because that will not cause any problem to our binary search tree. Awesome. So now return r at the very end. After we do this right there, return r. The next thing we do. Okay, so return the address of node 7 back up to the parent. For the parent level, we're going to be right here now. Right there. So we have r left equals insert r left. Well, the insert function returns basically the address of node 10. Oh, sorry, node 7 is returned, sorry. So what happens is, right, made a recursive function call, it returns the address of that node 7, and it will assign r's left to equal that node 7. So r left will be assigned to the same node that already was assigned to. That's okay because it's not going to break the binary tree. Everything is still just fine. After we do that, r left equals insert r left 9, then we have to return r back up to the parent. So at this level, we're at the root now. So now I happen to go back to the very first function call, go back to the root. So if I say root equals insert root 9, well, it returned r in that function call. So 15 is returned back to the root. And the root will be reassigned to the same node it was assigned to before, which doesn't cause any problems. So all we do is we find that hole in our tree, that vacant spot, and return that back to the parent. The parent will catch that node to left or right side, and then we simply just reassign the parent nodes left or right to point back to the same node that it pointed to before. So this insertion could be implemented using a void function instead. But we do it like this only because for a self-balancing binary search tree, so when we have to balance the tree in certain situations, then this method makes it very easy to actually handle that. But that's how we do an insertion. I'll do another example for sure, but any questions so far? I will definitely do another example, definitely, just to give us an idea, just to kind of help us understand further. But just any questions for right now? Copy this example. It's a little confusing, but that's sort of the best way to implement this structure for this insertion. See, I see a question here. So I'm not getting any sound on WebEx right now. So now I'm getting sound. Okay, let's take a look. So what if you had to assign element to the middle of the tree? Would you need to swap nodes around? Well, if you want to, so you mean like insert, or just if you want to you want to reassign something? If you do, you can just go ahead and go to that node and just reassign that node, or just reassign a key value to a new key. But typically for a search structure, you're not going to ever update the keys ever. If you do that, it's going to cause all kinds of issues. You're never going to ever reassign a key in a search structure. You can insert, find, or you can delete, but never reassign the key. That's going to cause all kinds of issues. So for insertion, no matter what we do, we always have to insert a new leaf node. No matter what, we're never going to insert in the middle ever. We always insert somewhere at the leaf level. If that makes any sense. Okay, cool. If you want to insert 4, you have to, okay, you know what? Let's insert 4. Let's do that right now. So let's go ahead and insert 4 and see what happens. So I'm going to erase all of this stuff so I don't have to redraw the entire tree. I can probably zoom in on this tree a little bit. So I'll rewrite this. So it's going to look more consistent. So 9 goes over there. Go ahead and zoom in on this. So now let's go ahead and just take the request here, and I'm going to insert 4 into this binary search tree. Okay, so we start off by just, again, we call the function root equals insert root 4. See what happens when we do this. So obviously R is going to point to that node right there. You first check, well, is R equal to null? And it does not equal to null. You check the key. So R arrow key is 15, which is going to be larger than 4. So obviously, if 4 is to be inserted, it must go to the left side of 15. So we're going to end up doing the following. We're going to say R left equals insert, pass in R left, and pass in the same key 4. So by calling insert passing in R left, we're going to spawn a function call, and this function call R will point over there. So again, we check, is R equal to null? It's not. And the key value 4 is going to be actually less than 7 once again. So once again, we're going to have the following. We're going to go ahead and say R left. Try to fit this here if I can. Insert R left. Or, sorry, let me try to rewrite this if I can. Well, looks kind of awkward, but not as awkward as this Sunday's game between Tampa and New England's going to be, but still same, looks kind of weird. But anyway, so now we're going to go ahead and respawn insert and pass R arrow left. So what's going to happen now is we're going to have R pointing over here. Now we check, R is not equal to null. And then we're going to have it where now in this case, the key value, which is 3, is going to be less than that 4, that parameter 4. So we have to go ahead, and this is going to be weird, but I'm going to go ahead and say R right. I'm going to write this to the left of it, but we're going to assign, because we know that since 4 is bigger than 3, that means 4 has to go somewhere to the right side of that node 3. Either directly to the right or somewhere to the right it's going to have to go. Equals insert, I'll sort of put it like this. 4. Okay, so now what's going to happen is in this situation, R is not going to equal null. I put it way down here just as I have some room over here, but the right side of 3 is definitely null. So we hit that if statement if R equals null. We hit that base case. So what happens is we're going to create a temporary pointer. Call it temp. And we're going to have it point to a node. We're going to create a new node. And we're going to set the key value to be 4. And we're going to set the left and right to both be null. And of course, we could set the value to some default, but we're not going to focus on the values. And that's it. So then return temp, which is what the function code is going to do, return temp. All right, return temp. So then temp is returned back to the previous function call. The function call above is right here. We're going to go back to this function call. We last left off on that line. So the insert function, we called recursively, it returns a pointer. What did it return? It returned the address of 4. And we're going to assign this node's right side to point to 4. So it linked that 4 to our tree. Okay, good. At least it makes sense. That's the important part. So, and then of course, after we assign R right equals insert, we're going to return R. Return the address of this node. R is pointing to that node. Return that node's address back to the parent. To go back to the parent level, we're last stuck over here. So R left will be assigned to whatever insert returns. Well, insert return the address of node 3. Because in the child level, it simply returned R, return that R up to the parent. So R left, in this case, is going to be assigned to that node, which is fine. We want it to do that because that's not going to cause any kind of problems. So that's all good. After we assign R left equals insert, okay, now next step is return R. So return the address of R up to the parent. The parent level, we're stuck right here. We're going to assign the parent node's left equal to whatever we returned over here. So we return the address of node 7 is returned back up to the parent. So the parent sets the left to point to that same node we pointed to before. Again, does not cause any problems. After we do that, return R once again. After we set R left equals to insert, return R, return the address of node 15 up to the root pointer. At the very top level, at the root level, turn the address of node 15 to the root, so the root will be reassigned the same node it was already pointing to before, which again does not cause any problems. So it's kind of a little bit strange. Hopefully this makes sense. A very strange implementation, but it turns out that this is the best way to do it if we have to do any types of, if you have to do any kind of work on our binary search tree, then this method does make, I mean, I'm not going to write the code for this other sort of tree, but I'll kind of paraphrase the code, but doing this method makes it very simple to implement this sort of self-balancing work on a binary search tree. So any questions on how this insertion works? Hopefully it's making sense. But I'm not going to have really trace out the code that, explicitly on the exam. If you understand the layman's terms of how we insert, you're kind of okay. So for example, if I insert 24 into this binary search tree, well, where would it go? Obviously, we have to start from the top. If we insert 50, you look at 15, 24 is bigger than 15, is bigger than 20, less than 25, so 24 would go over there. So if you understand that, you're okay. This code is more the nitty-gritty details, if in case you were wondering. But just, I think the important part really, truly is to at least understand the layman's terms of where we insert. We got to start from the root, and the key values at every level give us a guide as to where we have to insert left or right side accordingly. So I see a question here. Let's what we have here. Ah, I see. So what happens if let's see, I think so I have a question. What happens when we insert a value that's already in the binary bin tree? Okay, so what happens then? Well, our code actually would not even do anything. It would, because it's not, because if SA equals, let's say the key equals K, it wouldn't be less. But in this situation, it was still inserted. So the idea is if it was a duplicate, you have to have a special case where if our key equals that K value, return immediately. You don't want to have duplicates in a search structure. If you have more than one element, more than 1.7, it can be implemented, it can be done, but it's going to cause a lot of problems. You don't want to have duplicates in a search structure ever. So what you would do is literally say at the very top, if our key equals that K parameter, return R immediately. Just return R. Just get out of this function. Don't do anything because you don't want to have duplicates. Because imagine a search structure maintains students in a database. Let's say for MyUNLV, and we have a duplicate student. Then we trying to enroll a student into a class. Well, there's duplicate students. How do we distinguish between one of them? Well, we can't. So it's going to cause issues. You have to be able to distinguish different elements, different keys in a search structure, or else it causes problems. Let's say we have two people with the same last name, but different student ID. Okay, fine. You can distinguish them in some kind of way. You have to have some way to distinguish the keys, or else the search structure is going to be wrong, invalid, or whatever. So you cannot have duplicates. You just have a special case to handle that, and that's it. If you want to insert 8, let's see. You could. So if you want to insert 8, for example, where would 8 go? Well, start from the root. 8 is less than 15, larger than 7, less than 10, less than 8, so less than 9, sorry. So 8 would appear on 9's left side if you were to insert 8. Just follow these nodes are like guides, basically. Less than 15, larger than 7, less than 10, less than 9. So 8 has to be 9's left child. That's all you would do. We just find a vacant, we gotta find some vacant leaf area. And 9's left side is only spot where 8 could actually go. So binary search tree itself is a good basis to start off with, but you wouldn't really directly use this anywhere. So the two main type of search structures you use in kind of practice as a hash map is very popular use, and also a B tree, which is sort of a search structure tree, but each node contains a lot more elements than just one key value, which is more applicable to relational databases, which you learn about that, at least I teach that in CS477, but this is actually kind of like the basis for how we sort of construct search structures. But I mean, it could be used in industry and in practical situations, but really a hash map is more applied, is much more usable, and a B tree. So a 2-3, or not even a 2-3 tree, but a B tree is a tree where each node can contain a lot of elements. So if you're looking at a relational database and you want to find multiple entries, it stores a lot into one node. So then the lookup times will be faster if you're trying to find multiple entries at one time. So B trees and hash maps are kind of more practical for big amounts of data, but this is sort of like our basis. And we also could implement a B tree in a binary search tree type of order, but this alone is just sort of our basis for where we can, do more search structures. Yeah. Yep, you got it. Alrighty, so let's go ahead now and just go over what's the insertion runtime for a binary search tree. So, well, I mean, it's really kind of a no-brainer in a sense, but let's go ahead and just sort of, didn't want to draw space patterns. So let's go ahead and go over runtime analysis, time complexity. Insertion. So basically, you have to first perform a find operation. You have to use find in a sense. You have to find where would this key ought to go in our existing binary search tree. So we have to first do find, which really takes O of, well, remember it takes O of log n, or it could take O of n, depending on the height of the tree. So typically a height will be logarithmic, but there's no guarantee to get a nice height. So it's really O of log n or O of n, but we'll consider the worst case. So it'll be O of n because that's the worst case. And of course you have to consider the worst case. And then to insert a new node, well, that's going to take just O of 1 time, constant. Because, well, maybe that keyword new does a lot of things in the background, but we can't really do anything about that. And at the same time, whether our tree is bigger or smaller, that new keyword does not make any difference. Or maybe it does, because if you have a lot of elements already used up, it has to search through our memory to find vacant spots. But I guess it's more hardware level. We can't really improve that ourselves. So we'll assume that, well, we'll say constant because we can't do anything with that. So we'll say the runtime for allocating a node will be constant, we'll say. So we first do our find operation, and then we insert the element. So the runtime depends really on that find operation. That's the real bottleneck for insertion. So overall runtime, well, it's the best case, so it's going to be O of log n. Best case, maybe an average case, maybe, but worst case, though, it's O of n. Because remember, we have to, in the worst case, do exactly the height of the tree number of steps. Because in the worst case, you have to insert to the very bottom of our tree. That will take exactly height of the tree number of steps. And the height of the tree in the worst case could be O of n. So it'll take O of n steps to insert an element. If it's a nice and balanced binary search tree, then it will take at most height of the tree steps, but height of the tree would be log of n. Again, it depends solely on the height of our tree. So I'm going to cover one last sort of concept here, and then we'll go over a more complicated binary search tree structure. let's go over one last sort of topic. So I'm going to introduce another sorting, not one more. We'll cover another one after this, but not. So we're going to cover another sorting algorithm. I'm not going to go over it in detail because I'd rather move ahead here. But we actually have the following sorting algorithm, which will be known as, I think it's called binary tree sort, but it actually uses a binary search tree. So it's going to basically, it uses a binary search tree. So what happens is if we're given n elements to sort, we build a binary search tree of n elements of those n elements. Yeah, first. So what's the runtime to construct a binary search tree? So assuming we have an empty binary search tree initially, what's the runtime to construct this binary search tree? So I'm going to go ahead and show two examples so we can see what's the runtime going to be. So suppose we want to construct the following binary search tree given these elements. Let's say for right now, I want to insert this. I want to insert 1, 2, 3, 4, and 5. Now it's already a sorted array, but let's go ahead and insert these elements. So if we insert these elements into our binary search tree, we're going to first insert 1 at the root level, because if our tree is empty, the first element will become our root. Then we insert 2, is the right of 1. We insert 3, right of 2, I only can go over there. If we insert 4, remember how this works, we compare 4 to the 1, larger than 1, larger than 2, larger than 3, so 4 has to go over here. We insert 5, we start from the root, 5 is bigger than 1, 5 is bigger than 2, bigger than 3, bigger than 4, so 5 has to go over here. So we could have this situation. So the runtime to construct this tree, well, we can kind of look at it in the following way. So each insertion takes linear time. We insert n times, so take all of n squared. Now, of course, you can use Gauss's formula to really model this better. So the first iteration takes 0 steps, empty tree. Then it takes 1 step to insert 2, 2 steps to insert 3, 3 steps to insert 4, and 4 steps to insert 5. That's actually Gauss's formula. We can also use that. That's actually the more accurate runtime, but we can guesstimate it to be just, well, each insertion will take linear time, do n of those, so n squared. So that's a simpler way of guesstimating this, but the Gauss's formula is the more accurate sort of runtime. But we know that Gauss's formula is going to be quadratic, so we don't have to really think about that. So if we insert like this, it's going to give us n squared. So the order in which we insert into a binary search tree does matter. If I inserted the smallest element first, it'll be the root, and that's going to make a very high probability that, well, not high probability, we're guaranteed that the right side will have all the elements being the right side, so the tree will be very not balanced. So the smallest element or biggest element is at the root, then that means the tree will be very lopsided. So the order in which we insert does matter. So ideally, it's better to insert the median of the list first. There's a higher probability of having the two sides of a tree have equal elements on both sides to achieve a balanced tree. But the problem is we're at the mercy of hoping that please insert in the right way, which is kind of terrible to think of it like that. We're hoping that maybe relying on somebody else to insert nicely for us. And one thing in life that I've learned is, well, no, it's a very dark thing to say. Never mind, I'm not going to say that. So let's go ahead and go over another example as to how to insert into a binary search tree. Let's insert in different order and see what happens here. Let's insert 3, 2, 1, 6, 3, 2, 1, 5, 4. Yeah, I think that works. If I insert 3 first, well, 3 goes to the root. If I insert 2 next, 2 goes over there, and 1 goes over here. Following the same pattern, so you first insert 3, then we insert 2 next. 2 is less than 3, so 2 must appear on 3's left side. Then we insert 1. Well, 1 is less than 3 and less than 2, so 1 has to appear on the left side of 2. Then 5 is bigger than 3, so 5 goes over here. Then we insert 4. 4 is larger than 3, less than 5, so 4 appears over there. So this tree is definitely much nicer. This one is actually a balanced binary tree. So in this situation, each insertion takes logarithmic time, and we perform n insertions. So this will give us O of n log n time to construct this tree. Or we can think of it as, well, it'll take log of n factorial because we first do 0 steps, then plus log of 1, plus log 2, plus log 3, plus log 4. So we're going to have log of n factorial number of steps, and we've already proven earlier using the integration approximation that this would give us n log n. So we also can guesstimate this and say, well, each insertion takes log n time or logarithmic time. We do n of those to n log n. So yes, so in the worst case, it'll take n squared time to build up because we're basically, think of it as we're inserting an element to the back of a linked list where we don't have a tail node. We have to traverse the entire list because we have a very bad scenario. We have to compare all the elements. And no matter what, for a binary search tree, worst case, we have to go through the height of a tree, number of steps to insert something. It was very unbalanced. We have to go through every node potentially, which we did in earlier examples. So it's n squared because it compares every element, and n log n because we only had to do log n number of comparisons in the worst case. So, or in the best case, we didn't have to do more than log n comparisons. Whereas in the worst case, we had to do no more than n comparisons, which is not really good. So we do this log n work n number of times if it's balanced. Unbalanced, we do that O of n work n number of times, so it's n squared. So the real idea here is it balanced or is it unbalanced? If it's unbalanced, it'll take linear time for every insertion, so n squared. We do n insertions. If it's balanced, each insertion takes log n time. We do n insertions, so n log n. Yep. So now we go back to our original sort of algorithm. So we first give an elements and we build a binary search tree. And after we build a binary search tree, all we have to do is run in order, output the elements, output the elements using in order traversal. So that's the idea. And if we output a binary search tree using in-order traversal, it will output the elements in sorted order. So I didn't go over in order in class, but in order is like pre and post order, except that we first recursively call in order on R left, then see out R item, and then call in order R right. So if we do that, that traversal, it will definitely output a sorted list. So this part takes O of log, O of n, sorry. This takes O of n. Now remember, for in order, pre-order, post-order, it does not matter if a tree is balanced, unbalanced. It will always take O of n time no matter what. It does not matter what the tree shape is, balanced or unbalanced. But the real runtime depends on the time it takes to build our tree. So the overall runtime, runtime, well, takes, following. It's going to be O of n squared or O of n log n plus that O of n time to run in order. So really, O of n log n and O of n squared are both bigger than O of n, so that in order traversal part does not play a role really. It depends really on that time it takes to build our tree. So because we cannot guarantee that the height will be logarithmic, this takes O of n squared time overall. So binary tree sort is O of n squared because we cannot assume that a tree will be nice and balanced because of that fact. If we can assume the tree will be balanced, then yes, it'll be n log n to build our tree plus O of n time to run in order. Therefore, the runtime overall will be O of n log n. That's only because we can assume that. But because we can't assume that the tree will be nice and balanced, it's O of n squared. That's the runtime. All right. So we went over binary trees. I didn't go over deletion from binary search trees. It'll take too long. So I guess I reserve that for at least if I teach 477 again, then I kind of reserve that deletion for 477. But for right now, I guess the important part is understanding how we do insertion and find. So, okay, now we covered the basics of binary search trees. So now we're going to talk about a different type of binary search tree. So right now, every instance of binary search trees, it depends solely on the height, and that's going to be the real key to the runtime for binary search trees. The problem is that, well, every single instance, we had these two different possible heights, O of n, O of log n. And every time, we have to be pessimistic because we can't assume the best case happens, so we have to assume the worst case and always assume that the height is O of n. So a lot of these algorithms we've done so far, it has no real improvement because, well, okay, fine. We can hope that the height will be logarithmic and get a good runtime, but we're just sort of hoping. We're at the mercy of what the order of our insertion is, which is great, I guess, but wouldn't it be nice to be able to have a case where we can maybe guarantee that the height will be better than O of n? That's our kind of hope right now. So what we're going to do now is go over a binary search tree that can actually self-balance. Whenever the height is when the height is kind of bad, we balance it. So here's our next topic, which will be AVL trees. Let's go ahead and make a new page over here. AVL trees. I guess the name AVL comes from, I suppose, the researchers who discovered or created this mechanism. The last names were A, V, and L, so AVL. I guess I'm not sure what the actual, but it's AVL. It's based on the last names of the researchers who discovered this mechanism. So AVL tree is going to be a binary search tree. So the same property applies to an AVL tree, just like a binary search tree. However, it's going to be a self-balancing binary search tree. So balance happens. So we use a series of operations known as rotations. Um, Fix the tree when unbalanced. Okay, unbalanced. What does it mean to be unbalanced or balanced? So let's go over an example here. So I guess what does it mean to be balanced or unbalanced? So I'll define this in a second, but I'm just going to go ahead and draw some example trees and see if we can tell if it's balanced or unbalanced. Let's see what seems balanced or unbalanced to us is the important part before we go into the all the the actual more technical details. So the tree you see right in front of you, right there. Do you see that tree? That empty tree that doesn't exist? And the question is it balanced? Is it balanced? And the answer is, well, yeah, I guess it has to be. It's empty, so there's no way it can't be unbalanced. So empty trees are balanced. So good. So far we're on a good we're on a good doing pretty well so far. How about this tree with one node? Is that balanced? Well, we can't really say it's gotta be balanced. I mean, you can't if there's one node, you can't really say it's unbalanced. If that was the case, then this whole entire lesson on AVL trees goes out the window. So obviously one element has to be balanced. So okay, so now I'm going to have the following tree. Is that balanced? Well, with two nodes, you can't do better because, well, that's all there is with two nodes. So, okay, fine. So here's an obvious one. Is this one balanced? Well, I really can't argue that's not balanced, so that's good. So far, these are all balanced. And then let's look at some more examples. Is that balanced? I mean, once again, we can't do better than that. So it definitely has to be balanced. Now, what about this example? Is that balanced? I mean, it looks like it's sort of getting a little bit lopsided now towards one side. I mean, this was okay right here. This example on the left was okay, but yeah, we're starting, this is kind of getting a little bit out of whack. So this actually is unbalanced. So it's going to be unbalanced. So we're good. These ones will say are balanced. So obviously we can use our sort of kind of use our gut instincts and say, well, yeah, this one seems to look unbalanced. But of course, in computer science, with algorithms, we want to be more sure than just say, well, you know what, it looks unbalanced. Well, okay, well, I mean, that's good, but we want to really have a sort of a nice metric to use to determine balance. So what's going to happen is we'll do the following. So um, to have a balanced binary search tree for each node, the height, sorry, the difference of the left subtree and right subtree height and be off by at most 1. So if we have this property, then we have an AVL tree. And this is not going to guarantee a perfect balance, but it's going to be pretty good. I mean, there's a good chance it's going to be better than O of n. So it won't be perfect, but not bad. Good enough is the actual word, but good enough as in it's going to be pretty good. It's a good property to maintain. So what we have to do is we have to basically maintain, so every single node has to maintain its own height. So we're going to have to add, so in our binary tree node, remember we have our key value left and right. We're going to have to add a height field to each node. So it could be integer type. So each node has to store some integer, essentially, which I guess the integer values could get very large over time. So because basically we're going to use probably base 10 representation for our numbers, then as n gets very large, the number of digits to store a number into each node will take log 10 of the number of nodes you have, basically. So the size of this height could get pretty large. So the memory will get a little bit, it'll waste more memory because the number of digits could start getting large if n gets very big, if number of nodes in our tree gets very large. So that's kind of our downside. We have to have more memory because we don't want to constantly recompute the heights over and over again. We want to have the heights stored so we can very easily look up what's the height of our left and right subtree. So we'll do examples of that in a second, probably not today, but let's go over just rotation content. But anyway, that's the idea. And also, an empty tree has a height of negative. So a leaf node, a single node, has a height of 0, essentially. And its two subtrees have both heights -1, because for a leaf node, the left and right are going to both contain null. So the two heights are both -1, which means that it's balanced. At this, looking back at our examples here, let's say for this example, the left and right subtrees are both -1. Here we have a height of 0, 1. So at the root level, the left subtree's height is 0, and right subtree's height is -1. Difference will be 1. Example right here, for this node, the left subtree height will be 0, and the right subtree height will be -1. Difference will be off by 1. At the root level, the left subtree of the root has a height of 1, and the right subtree has a height of 0, so difference will be 1. And for this situation over here, for this subtree, or for this right here, the left subtree has a height of 1, that's 2 nodes, height of 1, and the right subtree height of this node has a height -1, difference is off by more than 1. That's why it's unbalanced. So for this node right here, also for root level, but this level, we can see right here, even before we hit the root, you can see at that level, left subtree has a height of 1, and the right has -1 for its height. So difference will be 2 in this case. So that's why it's unbalanced. All right, so let's go ahead and now talk about rotations. So this is going to be the key to maintaining a balanced binary search tree. So given the following tree, so we're going to have K1 and K2. This is going to be basically sort of Rick and Morty Bushworld Adventures, where every single frame has different animation. That's what's going to happen right now because I can't be consistent with these drawings to save my life. So basically, this will be very it's going to be very Bushworld Rick and Morty essentially. So we're going to have the following scenario. We're going to have the K1 and K2 are just nodes in our binary search tree. And X, that's going to be an entire subtree. So K1, K2 are just nodes. X will be an entire subtree. Then we'll have Y. Then we're going to have the subtree Z or Z. Yeah, Bushworld Adventures. Here we go. So right now, in this situation, we have an imbalance. So K1's left subtree has a certain height, and K1's right subtree is much bigger. So think of a binary search tree as like those old-fashioned scales. It's lopsided. We want to sort of fix that lopside, basically. So what we have to do is lift up the right subtree of K1 and lift down the left subtree of K1 to kind of fix this imbalance. So when this happens, we have an imbalance right here. So the right subtree of K2 will get lifted above K1. So the way this works, so rotation is a very simple operation. So this will actually be a left rotation. Put here, left rotation. So for left rotation, it means that the right subtree is larger. So you left rotate to fix that right subtree imbalance. You have to counter that right imbalance with a left rotation. So how does that actually work? Well, it's very simple. So K1 could be the root, or K1 could be some child of a different different node. So over here, what's going to happen? Let's zoom out a little bit. To rotate this, well, K2 is going to move up above K1. K1 will fall below. So the idea is that we're going to update this pointer. The K1's right pointer is going to point to K2's left subtree. That's what we do. So will that actually cause any problems? Well, if you look at it, the left subtree of K2 contains Y, and since we know that Y is on K1's right side, therefore anything to the right of K1 has to be bigger than K1. So if I set K1's right pointer to K2's left or right subtree, doesn't matter, either subtree will contain elements bigger than K1. So if I do that, it will not cause any problems because Y has to contain elements all larger than K1 because Y is on K1's right side. Not direct right side, but it's on the right side somewhere. So it cannot be smaller, obviously. So doing this is not going to break this this binary search tree structure. So I'll put it like this to like make a little room. And then K2, we're gonna set K2's left pointer to point to K1. Does that really break any? Does that violate the binary search tree rule? Well, since K1 is on the right side of, sorry, since K2 is on the right side of K1, that implies K2 must be bigger than K1. So if I make it where, what if K2 would be the parent of K1, and K1 will be the left child of K2, it does not violate the binary search tree order. Just think about it. It's not going to. And then we're going to return K2 back to the parent. The parent that was pointing to K1, well, now it's going to point to K2 from now on. So typically, we insert to a binary search tree, you always return the same node back up to the parent. But now we're going to return the right child of K1, return that node up to the parent. So K2 will get lifted above. So all we're going to do basically is adjust K2's left pointer to point to K1. K1's right child will now be K2's left. And then take K2, grab it, and lift it up. Everything will kind of fall below, which I can do a nice animation of that. I should have like, I don't know, anyway, that's the idea. So imagine I'm going to grab K2 and lift it up. What happens? K1 falls below, Z falls below, and Y falls below, but Y doesn't appear on K1's right side. So if I lift K2 up at the very end, I'll end up getting this final result. K2, we're going to have K1 over here, and Y will be on right side of K1. A terrible drawing, but it's not really scalable, not scaled at all. That's the result, and we'll do an actual example later on this, but this rotation will fix the imbalance. The whole idea, is that K1's right side was too big, so we had to essentially lift that up and bring down K1's left side to fix that balance, is the idea. And all we had to do, literally, was just set K1's right equal to K2's left. And then set K2's left equal to, K2's left equal to K1, and then return K2, the parent of K1. So remember, we return R back to the parent when we actually when we insert. But instead of returning the same R pointer, return R's R's right child, return that address up, which means that's going to get lifted up. That's going to be the new child of K1. So K1 parent now is going to be so K2 is going to be the new child of K1's parent, of K1's previous parent. That makes sense at all. Simply all we do is assign these two pointers. So K2's left points to K1, K1 right points to K2's left, and then lift K2 up. Is the idea. That's how we do a left rotation. So now let's go over a right rotation, and then that will be done for today. And then we'll continue and go over examples of AVL trees next time. Let's go over next example, right rotation. Same as left rotation, but a little different. And then we can sort of end this at a few minutes left. I'll try to finish this up as fast as I can. So now we're going to have K1 again. I'm going to go ahead and I'll draw a line. All right. So K1, we have K2 over here. We have K1's right side. Let's have it be Z again, or Z. K2's left. We're going to have a Y over here. We have X over here. So we have, again, the left side of K1 is now too big. It's unbalanced. So we have an imbalance right here at this level. And K1 there's something pointing to K1, either a root pointer or there is some parent of K1, again, like last time. And then we see that the left side of K1 is larger. So you have to right rotate to fix this imbalance. So what we have to do is same idea as before. We're going to first set, so K1's left pointer is now going to be pointing to K2's right side. Once again, this will not cause any problems, because since y appears somewhere on K1's left side, everything in the subtree y has to be less than K1. So having it to the left of K1 is not going to violate our binary search tree property. And then we have to set K2's right to point to K1. So since K1 was a parent of K2, and K2 was the left child of K1, that means K2 has to be smaller. So if K1 would be the right child of K2, that would not break the binary search tree order. Just think about it. It will not violate anything. So whether K2 is a left child of K1, or if K1 is a right child of K2, either way is fine. It's like having this. It's like saying if I have 4, then 5, or if I sort of make it where I have 5, then 4, it's not going to break the binary search tree order. Oh, wait, what the heck am I doing? Whoops, my mistake. Whoa. Bad example. So we have a case where it's supposed to be actually 5, then 4. My mistake. So right there, a binary search tree. If I go ahead and do like this, it's still going to be a binary search tree. It didn't violate anything. So doing that is actually just fine. So after we do that, we simply return K2 to the parent. So the parent now point to K1. Now it's going to point to K2. In other words, once we update these two pointers, we grab K2 and lift it up. Everything will just fall below, basically. So K1 falls below, just like that. So the result will be, put this, I guess, over here. The K2 gets lifted up. K1 falls below. X will still remain below. That's going to still not change. X will still be below K2. Z will still remain right here. And Y remains right there. Very bad drawing, but that's the end result. Terrible drawing. This is the Bush World Adventures of 302 class right now, but the result is essentially that. So it's very simple to maintain a rotation, very simple to rotate. All you have to do is update two pointers and return a different pointer, different node to the parent, which will essentially have that K2 get lifted above K1. So instead of returning K1 back to the parent, we return K2 to the parent. So K2 is now going to be the child of the existing parent of K1. So it's a very fast operation, actually. It's just two pointer assignments and return different node back to the parent, and that's it. Very simple to rotate. So we're going to do examples of how this is going to work out on various scenarios. But for now, let's go ahead. I'm going to go ahead and stop right there. So yes, thanks for watching, you guys. Stay safe. Have an awesome weekend. And I will see you guys on Monday.